So today we're going to start things off with an example problem that I did not get to at the end of our last lecture. So let's say that we have a three-phase 208 120Y voltage source powers a 25 horsepower induction motor. Which draws a current of 75 amps RMS at a power factor of 0.85 lag. If the stator copper losses are P1 CU is equal to 1867 watts. The rotor copper losses are P2 CU is equal to 650 watts. The core losses are P core is equal to 1500 watts. And finally, friction and windage losses PFW are equal to 300 watts. Determine the following quantities. That is definitely a G and not a Q. So the first thing that I want us to figure out is the power delivered across our air gap, PAG. I want us to determine the mechanical power developed which is Pmech. I want us to determine the output power delivered to the shaft of the motor. Shaft. And finally, the efficiency of the motor. Yeah. All righty. So I'm going to redraw, because I didn't save it, our power flow diagram here so that we can figure things out. Okay. So on this side, we have our input power, and then we should have our stator's copper losses. Our core losses. Our rotor copper losses. Our friction and windage losses. Our stray losses. And then everything else is the amount of power that is delivered to the shaft of our motor. Just so that we recall, our air gap power is simply our input power minus our core losses and our copper losses in the stator. And then our mechanical power is simply our air gap power minus the copper losses in the rotor. Okay. So for the first part of our problem, we are asked to find the power delivered across the air gap. And we are told what our copper losses in the stator are and our core losses are, which means if we can figure out what our input power is, then we have enough information to determine our air gap power, right? So anybody have any idea how we might figure out what our input power is? So let me ask you guys this question in a slightly different form. What kind of power is our input power for this induction motor? Electrical, right? So it's going to be related to the voltages and the currents and the power factor. Okay. So because we have a three-phase induction motor, our input power is going to be 3 times the magnitude of our input voltage. And we're going to use the Y voltage for this because all of our equivalent circuits and all that kind of stuff were done on a per phase basis, which would be the Y representation, times our stator current, times the power factor at which our motor operates, right? So for us, that's going to look like 3 times 120 volts RMS times 75 amps RMS. And if our voltage source is supplying power at a power factor of 0.85 lagging, then our motor is absorbing power at that exact same power factor. Oh, and I shouldn't put lagging there. So this will give us 22.950 kilowatts of electrical power at our input From this, our air gap power is simply our input power minus our stator copper losses and minus our core losses, or 22.950 kilowatts minus our stator copper losses in kilowatts, so that would be 1.867 kilowatts. Come on, pen, right. And then minus our core losses, which were 1.5 kilowatts. And this comes out to be 19.583 kilowatts. So that's our air gap power. The next thing that we're trying to find is our mechanical power, right? So I'm going to write down a relationship here, and I'm going to explain why we can't use it even though we have it. So we know that our mechanical power is simply our air gap power times a factor of 1 minus the slip. However, we know nothing whatsoever about the rotation speed or anything like that of our induction motor. So we have no means by which to determine the slip. So instead, we're going to have to look at our power flow diagram again here. Our mechanical power is nothing more than our air gap power minus our rotor copper losses, right? So we can't use this guy, but we can use Pmech is equal to air gap power minus P2 CU. So 19.583 kilowatts minus our rotor copper losses, which were 650 watts, so 0.65 kilowatts. And this comes out to be 18.933 kilowatts. Using our power flow diagram yet again, our output power is nothing more than our mechanical power minus our friction and windage losses minus our stray losses. Since we didn't have any stray losses that are identified, we're going to assume they're 0 or negligible. And so we're just going to have Pmech minus P friction and winding. So 19.583 kilowatts minus 0.3 kilowatts comes out to be, I'm sorry, I put the wrong number here. The mechanical power is 18.933. Minus 0.3 comes out to be 18.633 kilowatts. And I didn't give myself enough room to write our efficiency, so let's just do it on the next page. Our efficiency, N, is simply the power delivered to our shaft, or our output power, they're the same thing, divided by our input power. So this is 18.633 kilowatts divided by our input power of 22.950 kilowatts, which comes out to be 81.19%. which is a perfectly reasonable efficiency for an induction motor that's operating somewhere close to full load. All right. So, anybody have any questions, comments, or concerns regarding that particular example problem? Hopefully fairly straightforward. Takes into the use that nice power flow diagram that we developed. All right. So now let's talk about what if we want to perform actual calculations on our induction motors, right? So right now, this is where I'm going to start talking about the Thevenin equivalent circuit. Of an induction motor. So right now we are dealing with effectively the transformer equivalent model, right? So something that looks exactly like the equivalent circuit of a single phase transformer. So we have our stator copper losses represented by R1. We have our stator leakage losses represented by JX1. We have a magnetizing branch here that takes into account our core losses. And our losses due to having to magnetize our air gap. So this is the rotor side, this is going to be the stator side. And then over here on the rotor side, we have JX2 prime, which represents the leakage currents or the leakage losses in the rotor, and R2 prime over S, which represents our mechanical power delivered as well as our copper losses in the rotor. So effectively the real power delivered across the air gap. And just for the sake of argument, this is where our air gap is. And I'm going to throw this in here. So this is our stator current. And this is our rotor current. Okay. So if we wanted to do analysis using this equivalent model, we could do it. It's not wildly complicated, right? It's just an impedance in series with two impedances in parallel. That being said, the math is going to get annoying and tricky looking at it from that perspective. So people smarter than me have come up with an equivalent circuit model that makes the calculations quite a bit easier, okay? So the first simplification that we're going to make is we are going to throw away our copper losses, or excuse me, our core losses, okay? So that's just going to move this branch here to the middle, like so. So let's talk about why we're going to do this, okay? So the first reason that we throw away our core loss resistance there is because when we perform a blocked rotor test, we can't extract out, actually, I think it would be the no load test, sorry. Effectively, we can't extract out what that resistance is by itself. So typically speaking, the losses that are associated with the core usually get lumped together with the losses that are associated with friction and windage losses, as well as stray losses to form what are called rotational losses, okay? So we can say that our rotational losses, P ROT, will be our core losses plus our friction and windage losses plus our stray losses, which can all be measured together with a test. So having the resistance RC in there doesn't add any value if the test doesn't allow us to extract out that particular part of it. Okay. All right, so from here, things are arguably not any better. There's one less element, but it's still an impedance in series with two impedances in parallel, okay? So this is where Thevenin's theorem comes in. Anybody remember what Thevenin's theorem is from your circuits classes? Everybody's shaking their heads, no. Okay. It's been a minute.
Pretty sure we asked for explanation and
All right, so, well, then I'm going to explain what Thevenin's theorem says, okay? So Thevenin's theorem is actually pretty amazing. It says that if we have a two-terminal electrical network, we can replace it with an equivalent circuit that is nothing more than a voltage source in series with an impedance. That is it, okay? So effectively, I can make, let me put my terminals here in blue, okay? I can make everything to the left of that blue dashed line, which is effectively just the equivalent circuit of our stator, look like nothing more than a voltage source in series with an impedance. That equivalent circuit would then be connected in series to the impedance that represents our stator, so that we have a simple single loop circuit where it's just voltage source in series with our Thevenin equivalent impedance in series with our rotor impedance. And analyzing that circuit where everything is in series is a heck of a lot simpler than analyzing this, which is why the Thevenin equivalent circuit was developed, okay? So our Thevenin equivalent circuit will look like this. So we're going to have a Thevenin voltage in series with some Thevenin resistance, which is in turn in series with some Thevenin reactance. Now we've effectively hit our air gap. So here's JX2 prime. Here's R2 over S primed. And I'll use blue again. So everything to the left of the blue dashed line here is electrically equivalent to everything to the left of the blue dashed line above, okay? So this is us using our Thevenin equivalent circuit. Now, the problem now is, how do we figure out what V Thevenin is, what R Thevenin is, and what X Thevenin is? Okay, we're going to apply Thevenin's theorem. So I'm looking just at my stator effectively right now. And I'm trying to figure out what my Thevenin voltage is. Okay. Well, by definition, my Thevenin voltage is nothing more than the open circuit voltage across my terminals of interest. And now I'm simply going to solve for what that voltage will be. So to me, this looks like a voltage divider circuit, or really, yeah, voltage divider circuit using impedances, right? So using voltage division, I can say that my Thevenin voltage is just going to be the voltage applied at my stator, V1, multiplied by my ratio of my impedances, which in this case is simply JXM over R1 plus JX1 plus XM. Because those two reactances look like they're in series from the perspective of our voltage source, okay? So that's my Thevenin voltage, but we are going to be using usually the magnitude of our Thevenin voltage. So do you guys remember how to take the magnitude of a complex number? Pretty much. That'll work. So the magnitude of our Thevenin voltage is going to be the magnitude of our applied voltage times, here we're going to have XM in our numerator, and then we're going to have the square root of the squares, like what was suggested, R1 squared plus X1 plus XM quantity squared. So this is the accurate representation of what the magnitude of our Thevenin voltage is going to look like. But we're going to simplify it further, okay? We're going to simplify it further by observing that R1 represents the resistance of our stator windings, okay? Which is typically pretty small, right? What was the resistance of our primary windings referred to the primary side on most of the transformers that we were dealing with? On the order of a couple of ohms tops. Very, very small. Our magnetizing reactance here is going to be much smaller than it was when we were dealing with transformers. But our leakage reactance, remember, is going to be higher than we used to see because we have to magnetize our air gap. So we are seeing the effects of that increased reluctance of our system, okay? So this is going to look like the magnitude of V1 times sorry, my stylus isn't writing. There we go. XM over X1 plus XM when R1 squared is much smaller than X1 plus XM squared, which will be true for practically every induction motor, okay? So this is technically introducing a little bit of error, but it's small enough that we don't care because the math gets easier. That sound reasonable? All right. So that's our Thevenin equivalent voltage and its magnitude. Okay. Now we need to find our Thevenin equivalent impedance. Okay. So our Thevenin equivalent impedance is found by looking at the stator of our motor. So here we have R1, JX1, JXM. We're looking in through the exact same terminals that we figured out our voltage at. So this is Z Thevenin. But we need to be looking at a dead network, which means that we need to be turning our voltage source off. And a voltage source that's off looks like a short circuit. So we short circuit our input terminals. Okay. What is this impedance? It's just JXM in parallel with our R1 plus JX1 impedance, right? So we're going to have JX1 times R1 plus JX1 over R1 plus J. Sorry, that first X1 is supposed to be an XM. JX1 plus XM. Okay. But we can simplify this too. Okay. So I'm going to have to go to the next page here because I'm running out of room. So when, which this will be true almost 100% of the time, R1 is much less than, or excuse me, R1 squared is much less than X1 plus XM squared, and X1 is much less than XM. Our Thevenin equivalent impedance is approximately R1 times XM over X1 plus XM quantity squared plus J X1. So the real part of this approximate Thevenin equivalent impedance is R Thev. And then we have plus the imaginary part, which is X Thev. Okay. So R Thev is R1 times XM over X1 plus XM quantity squared. And X Thev is just going to be approximately equal to X1. So now we have all of the different parts of our equivalent circuit. So let's put it into practice. Okay. Okay. So let's say that I wanted to figure out what my air gap power was, because that's a pretty critical piece of information, right? So if I look at my Thevenin equivalent circuit, where I have R Thev in series with JX Thev, here's my air gap. Here's JX2. Here's R2 prime over S. Here's where my air gap is. This is my current I2 prime. So we learned the other day that our air gap power is just going to be 3 times the magnitude of that current I2 times that resistance R2 over S. But now solving for I2 is significantly easier, right? So I2 is just going to be our Thevenin voltage divided by R Thev plus R2 over S plus J X Thev plus X2. magnitude of this current, doing the exact same thing we did with the voltage a few minutes ago, is just going to be the magnitude of our Thevenin voltage divided by the square root of the squares. R Thev plus R2 prime over S quantity squared plus X Thev plus X2 prime quantity squared. Let me make sure that that looks better too. And I take my square root over. So from here, our air gap power, which we know is simply 3 times the magnitude of I2 squared times R2 over S is going to be 3 times the magnitude of our Thevenin voltage squared, R2 over S divided by that denominator squared, which just looks like R Thev plus R2 prime over S squared plus X Thev plus X2 prime squared. So we can calculate our air gap power purely from knowing what the parts of our model are, right? No circuit analysis whatsoever at this point, okay? Well, if we know the air gap power, then we can figure out mechanical power and things like that as well. We can also figure out torque, right? Torque's a pretty important figure of merit for these motors. So let's develop an expression for the mechanical torque. Okay. So the mechanical torque delivered across the air gap, or the mechanical torque delivered to the rotor is the mechanical power divided by the angular velocity of the rotor, which we talked about in class last time. And we found out that this was nothing more than the air gap power divided by our synchronous angular velocity, which is a constant thing, which is good, right? We just figured out how to calculate the air gap power as well, so we're in good shape here. And so now we literally just substitute in our equation, right? So from here, it's literally this exact same thing that we have up above, except there's a factor of omega S in the denominator. So we're going to have omega S times R Thev plus R2 prime over S quantity squared plus X Thev plus X2 prime squared. That's what the hell just happened. Sorry about that. And then up in our numerator, we'll have 3 times V Thev squared times R2 prime over S. So what's interesting about this expression, or more interesting than the fact that we can relate every one of the parameters to our equivalent circuit model, is that this gives us torque as a function of slip, right? So we can figure out what our torque is at specific points, like what our torque is at startup, because we know that our slip is simply 1 at startup. Or we can use a little bit of calculus and take the derivative of our air gap power with respect to slip to find out when maximum torque is going to occur and what that maximum torque value will be. So just like you can find maximum power transfer for a circuit, you can find effectively maximum torque transfer using the same effective process, okay? So our startup, let's put this. So T max start, so this is our startup torque, is just T max evaluated at a slip of 1, right? Which means all of our R2 over S's are just going to look like R2s now. So we're in the denominator, we're going to have omega S times R Thev plus R2 prime squared plus X Thev plus X2 prime squared. Up here, we'll have 3 times V Thev squared over R2 prime. That's our startup torque. Again, nothing more than the equation we just developed, evaluated when our slip is 1 or our rotor is blocked, okay? For maximum torque, like I said, maximum torque is going to occur when the air gap power is at its maximum. And the air gap power depends on the slip. So we can say, go away thing, that the slip at maximum mechanical torque will occur when the derivative of our air gap power as a function of slip with respect to slip is equal to 0. Okay, not going to make you guys do the calculus or anything like that. The result of this analysis is that the air gap power is at its maximum when R2 prime over S is equal to the square root of R Thevenin squared plus X Thevenin minus so I have in my notes here X7 and minus X2 prime, but in the next step I have it as X7 and plus X2 prime. So I'm going to say X7 and plus X2 prime, and I might have to go back and fix this. We can rearrange this equation for S. And so the slip at which maximum mechanical torque occurs is going to be the square root of R Thevenin squared plus X Thevenin plus X2 prime squared. And we have R2 prime over this. Now, bear with me just a moment. I'm going to look at 2 textbooks that I have saved on my computer here because I want to get this right. Because actually, in my head, it would make more sense for it to be x thev minus x2, because that's the way that maximum power transfer occurs when you have impedances, is you need to cancel out the reactances in order to make the resistance part as large as possible, which is what we're trying to do here, okay? So I'm going to look at two different textbooks. I'm going to look at the official one for the class, which is riddled with errors, and then I'm going to look at a better one, and we're just going to see what happens. So textbooks. All right, so let's see. Our official textbook for this class is this one. And let me get my keyboard out. No. Table of contents. I hate that this does not allow me to scroll. Past transformers. Damn it to hell. We're on induction machines. Let's see, looks like somewhere around page 241. So it was lying. Past that. Here. Blah, blah, blah. And we're getting closer. Yeah, so it very much says x Thevenin minus x2 squared for equation 6.87. And then rearranges that expression, I believe, incorrectly to give us x Thevenin plus x2 squared. All right, so let's look at a different textbook on the same material. Let's see, PC Sen. Yeah. All right, so this guy says that it should have been x Thev plus x2 prime from the jump. Okay. So this guy says it's supposed to be a plus sign for all of the equations, so we're going to go with plus sign, and then I'll have to just derive the damn thing later. All right, so we're going to leave things as is. If we substitute in this slip value into our equation for torque, we get our maximum torque, which is going to come out to be twice omega s times r Thev plus the square root of r Thev squared plus x Thev plus x2 prime squared. Close this bracket. And then up top, we have 3 times the square of our Thevenin voltage. All right. So there is a distinct possibility that this is the end of what we're going to learn about induction motors, okay? I might talk very briefly about the tests that are performed to calculate the equivalent circuit parameters, but I'm not going to give you guys problems on that because I'm trying to pick up the pace because we're behind. And also I talked to Dr. Patari and he said he didn't think that it was necessary for you guys to know it. And he's taught the class before, so I'm just going to go off of his expertise. Excuse me. So what we're going to spend the next hour doing really is working a monstrous example problem that ties everything together. So that if you know what the equivalent circuit of an induction motor looks like, we can calculate its efficiency, its power factor, its torque, power in, power out, losses, all that kind of good stuff. Okay. So let's say that we have a 3-phase, 2-pole, 35 horsepower, 60 hertz induction motor, and it is connected to a 480 277Y volt RMS voltage source. And our motor has the following constants. Excuse me, that shouldn't be at. So this is per phase, so I want to be clear about that. Referred to the stator. So R1 is 0.322 ohms. R2 is 0.196 ohms. X1, that should be primed because it's referred to the stator. X1 is 0.675 ohms. X2 prime will be 0.510 ohms. And XM will be 12.5. We are told that the total rotational losses are 1,850 watts and assumed to be constant, effectively independent of slip. So this is our friction and windage losses, our stray losses, and our core losses all lumped together. And we want to find the following things. So for a slip of 3% at rated voltage and frequency, determine the following quantities. So we're going to find 12 things. This is all the, we could actually find more, but I ran out of time. Okay. So let's find our rotor speed, Nm, our rotor current, I2 prime, our stator current, I1, the power factor at which the motor operates, EF motor, power delivered across the air gap, EAG, the developed mechanical power, the mech, the output power, the shaft, the motor efficiency, N. These are all the things that we're going to find at our slip of 3%. We are also going to find the motor's starting torque, Tmax start, the slip at which maximum mechanical torque occurs, S Tmax max. We're almost done. The rotor speed at maximum mechanical torque. Go away that thing. And JKL. The maximum torque developed. What I was wanting to get to, but literally ran out of time, was also calculating our efficiency at maximum torque. The problem there is that it requires us to go back and recalculate several different things effectively, and so it literally would be a long process. So might do something like that on Tuesday. All right, so we have a litany of things to figure out, right? So this is damn near everything I could possibly ask you guys to calculate. All right, so let's get cracking. right? So the first thing that we're looking for here is our rotor speed, okay? So to determine our rotor speed for a known slip, we need to know what our synchronous speed is, right? So I am saying, here's our solution. So for part A, our rotor speed Nm is given by Ns times 1 minus S, right? This is an equation that we developed in class on Tuesday. How do we figure out what Ns is? Because the slip is given to us the same way we did on Tuesday, right? So Ns is 120 times our stator's excitation frequency divided by the number of poles. So that's 120 times 60 over 2, which is 3,600 RPM. So up here we can say that this is going to be 3,600 RPM times 1 minus 0.03, 3%. And I got 3,492 RPM. Part B, we are asked to find our rotor current. Okay. So our rotor current is I2, and we are going to use our Thevenin equivalent circuit in order to determine this quantity. Okay. So we need to figure out what goes into our Thevenin equivalent circuit. Our Thevenin voltage magnitude is the magnitude of V1 times XM over X1 plus XM. So this is 277 volts RMS. XM was 12.5 ohms. X1 was 0.675 ohms. So this comes out to be 262.808 volts RMS. Our Thevenin resistance, Rthev, is our resistance R1 times XM over X1 plus XM quantity squared. .322 ohms, 12.5 ohms over 0.675 ohms plus 12.5 ohms. That squared comes out to be 0.290 ohms. And the easiest part, our Thevenin reactance is just X1 or 0.675 ohms. So now we're trying to find our current. We have an equation for the magnitude of our current. I gave it to you guys earlier, so we're literally just going to apply it directly. Okay. So the magnitude of our rotor current is the magnitude of our Thevenin voltage divided by Rthev plus R2 prime over S squared plus X Thev plus X2 prime squared. And we take the square root of that whole thing. Substituting numbers in. I'm going to do the denominator first so I know how much space to take. So R Thev was 0.290. R2 was 0.196. S is 0.03. X Thev was 0.675. X2 prime was 0.510. And then our Thevenin voltage was 262.808 volts RMS. And so our current here comes out to be 37.948. My stylus will write. There we go. Amps RMS. All right. So for part C, we are trying to find our stator current. Okay. So there are actually a couple of different ways that we could find our stator current. All right. So bear with me a moment while I go back to the second page here, I think. Okay. So we are trying to find the magnitude of this current I1. We know the magnitude of the current I2, right? So we could effectively do current division backwards here to find it, right? Because we know that all of I1 flows through that impedance R1 plus JX1, and then some of it splits and flows through that impedance JXM. Some of it splits and flows through that impedance JX2 in series with R2 over S, okay? I'm not going to do that, even though it's actually pretty straightforward to do it that way. What I'm going to do instead here is I'm going to calculate the equivalent impedance of our motor as a whole. And then I'm going to simply divide our input voltage by that equivalent impedance, because that's going to give me my current I1. The reason why I'm doing it this way is because I'm asked to calculate the power factor next, and the power factor of our motor is just cosine of the angle of the impedance of our motor. So I'm killing two birds with one stone here, right? If I know what the impedance of the motor is, that lets me calculate I1, and it also gives me my power factor. So it's less work if I go this particular route based on the information that I'm trying to find, okay? So multiple different ways to skin this cat. I'm going with the one that gives me the most amount of information that I can use later so that I can be as lazy as possible. So our equivalent impedance of our motor is going to be R1 plus JX1 in series with JXM in parallel with R2 over S in series with X2, right? So R2 over S plus JX2. And those two impedances in parallel, so that's just my magnetizing branch in parallel with my rotor. Looks like this. Now, This is one of those places where I cannot encourage you guys enough to get a calculator that can do this math for you without having to do all of the terrible combinations and permutations and all that kind of jazz. So if I put numbers into this thing, this is going to look like 0.322 plus J 0.675. And then I have up here, J 12.5 times 0.196 over 0.03 plus J 0.510, all divided by 0.196 over 0.03 plus J 12.5 plus 0.510. And in polar form, I get a motor impedance of 6.265 angle 34.893 degrees ohms. And I want my answer in polar form so that I can determine my power factor very easily in the next step. Okay. So, knowing what our motor's equivalent impedance is, our stator current is simply our voltage V1 divided by the impedance of the motor. So it's going to be 277 angle 0 degrees volts RMS divided by that 6.265 angle 34.893 degrees ohms, which gives me 44.214 angle negative 34.893 degrees amps RMS. And because I was only looking for the magnitude, sorry, that should be 1. $44.214 amps RMS. So we're bringing back some circuits relationships here that I'm assuming you guys know. If anything seems wonky, please let me know and I'll be happy to explain it further. All right, so 3 things down, 9 to go. Yes, sir. Okay. So our equivalent circuit is on a per phase basis, right? So that means that we are looking at a phase to neutral voltage, which is the Y voltage. Because a delta is between phase to another phase, or it's a line to line voltage, right? So in all of these calculations, I need to be using Y voltages because that's what my equivalent circuit is using. So I could have converted the 480 delta voltage into a Y voltage, but that is exactly the 277 that I told you. So when this is just going to be me ranting about our textbook a little bit here. Okay. For whatever reason, our textbook always gives us the line to line voltage, 480. And then in the math, they always wind up going through and dividing by square root of 3 to get the Y voltage. Well, I am trying to be nice and I just give you both, but we're going to use the Y voltage every time, so that you don't have to wind up doing that step yourself, right? So common voltages here in the US, 480 delta is the same as 277 Y, 208 delta is 120 Y, and then there are others in different countries and all that kind of jazz, but that's mainly what we use unless we're talking about larger scale things. So because our equivalent circuit is a per phase system, which is inherently a Y connected system. And we know for a fact that our stator windings are connected in Y and our rotor windings are also connected in Y if we have a wound rotor. I'm just doing everything with Y voltages. All right, so part D, which was the power factor, right? So this is where finding out the equivalent impedance of our motor really comes in handy, okay? So the power factor of our motor will, by definition, be the cosine of the phase angle of V1 minus the phase angle of I1. But this phase angle is nothing more, or this difference in phase angle, excuse me, is nothing more than the phase angle of the impedance of our motor. From the definition of impedance, the phase angle of an impedance is going to be the angle of the voltage minus the angle of the current, okay? So that means we're just going to have cosine of positive 34.893 degrees, which gives us a power factor of 0.820 or 82% lagging. It's lagging because the angle is positive, right? The power factor for an induction motor should always be lagging because there aren't any capacitances. Everybody okay with our power factor calculation here? Anything wild or crazy? All right, pretty straightforward, I think, as well. So let's look at our air gap power. I'm going to go ahead and move to the next page just so that I can finish this step all in the same thing. So our air gap power, we're literally just going to use one of the relationships that we developed today, right? So from our Thevenin equivalent circuit, we know that our air gap power is 3 times the magnitude of the Thevenin voltage squared times R2 over S divided by R Thev plus R2 over S squared plus X Thev plus X2 prime squared. Throw numbers in here. It's going to be 3 times 262.808 volts RMS squared, 0.196 ohms over 0.03, our slip, divided by 0.290 ohms plus 0.196 ohms over 0.03 squared, 0.675 plus 0.510 squared, and we get an air gap power of 28.225 kilowatts. It's just direct application of an equation we derived earlier today. Our mechanical power developed is going to be a bit easier because we have a known slip, right? So our mechanical power is simply our air gap power times 1 minus S. this is going to come out to be 27.328 kilowatts. So for part G, we're asked to find our output or shaft power, okay? So we are going to refer back to our diagram. So I'm going to go all the way back to the first page here, and we're going to look at some things, okay? So we were told what our rotational losses are. So we know what the core plus the friction and winding plus the stray losses are, right? We found out what our stator current was, which means we can easily calculate what our copper losses are in the stator. We know what our rotor current is, so we can easily calculate our copper losses in our rotor. We know the voltage that's being supplied to the motor. We know the current that's being supplied to the motor. And we know the power factor at which the motor operates. So we can figure out the input power to the motor easily. And so simply the input power minus all of these other powers is going to give us our shaft power. So that's the approach that we're going to take. It's the easiest way to do it based on the information that we were given. Okay. So let's start with our input power. We have a three-phase system, so it's going to be 3 times the magnitude of our Y voltage times the magnitude of our stator current times our motor's power factor. That's 3 times 277 volts RMS, 44.214 amps RMS. Our power factor was 0.82. So I get 30.128 kilowatts. Our stator copper losses are going to be 3 times the magnitude of our stator current squared times R1. That's going to be 3 times 44.214 amps RMS times 0 squared times 0.322 ohms. And write down the numbers here so we make sure. Yeah, 0.322. Alrighty. And this comes out to be 1.689 kilowatts. We could write a similar equation for our copper losses in our rotor, but there's actually an easier relationship. Because we know our air gap power, our copper losses is simply the slip times the air gap power. Remember, that's a relationship that we developed in class on Tuesday. 0.03 times our air gap power of 28.225 kilowatts comes out to be 0.847 kilowatts. And tying things together, the output power at the shaft of our motor is the input power minus our total copper loss minus our rotational losses. So let me. Sorry, I'm looking, I want to look at that power flow diagram again, just to be on the safe side here. Yep, okay, so copper losses, input power minus copper losses minus rotational losses. Okay, just making sure. Throwing numbers in here, we have 30.128 kilowatts minus 1.689 kilowatts minus 0.847 kilowatts. Our rotational losses were given to us in the problem statement. They were 1.850 kilowatts. This comes out to be 25.742 kilowatts. And part H is our efficiency, which is nothing more than our shaft power over our input power that we just calculated. 25.742 kilowatts divided by 30.128 kilowatts. And so we're operating at efficiency of 0.854 or 85.4%. All right. So now we're in the home stretch here. The last few things all having to deal with operation at specific slips. Okay. So part I, we are asked to find our startup torque. And the startup torque depends on our synchronous angular frequency, right? So let me scroll back so that we see the equation here. So here's our startup torque. The only thing that we haven't already figured out in this equation is omega s. Everything else we've already determined, so it's just plugging and chugging once we figure out what omega s is. So how do we figure out the angular velocity of our synchronous speed? We did it on Tuesday. Just our synchronous speed times 2 pi over 60. So this is 3,600 RPMs times a conversion factor of 2 pi over 60 gives us 376.991 radians per second. 377 if you're feeling lazy, which is a very common thing to do, is just say, if you have a synchronous speed of 3,600, you just call your angular frequency 377 radians per second and call it a day. From this, our mechanical starting torque, so we're just using our starting torque equation now. So this is going to be 3 times the magnitude of our Thevenin voltage squared times R2 prime, excuse me. There is no over S here because at startup, recall that S is equal to 1. So we're going to have omega S times R Thev plus RS excuse me, R2 prime, I guess, squared plus x nav plus x2 prime quantity squared. Slapping numbers in this guy gives us 3 times 262.808 volts RMS squared times 0.196 ohms divided by 376.991 radians per second times 0.290 ohms plus 0.196 ohms quantity squared plus 0.675 ohms, 0.510 ohms quantity squared. And this comes out to be 65.670 Newton meters, which is the unit. Let's see here. We're on J now. For part J, we're trying to find the slip value at which maximum torque occurs. Okay. The equation that we checked 2 textbooks to make sure it was correct for was R2 prime over R Thevenin squared plus X Thevenin plus X2 prime quantity squared. Putting in our numbers, this looks like 0.196 ohms divided by 0.290 ohms squared plus 0.675 ohms plus 0.510 ohms squared. And our slip here is going to be 0.161. So 16% slip is when we have maximum torque, right? Our last 2 little things to solve for. Our rotational speed at maximum torque. This is simply going to be our synchronous speed times 1 minus our slip at maximum mechanical torque. 3,600 RPMs times 1 minus 0.161 comes out to be 3,020.4 RPM. So our motor slows down pretty significantly, well, obviously 16% from its synchronous speed in order to deliver maximum torque. And then our last thing here is calculating the value of that maximum torque that can be supplied by this particular motor based on its Thevenin equivalent circuit. So our maximum mechanical torque is given by 3 times magnitude of our Thevenin voltage squared divided by twice our synchronous angular velocity, R Thevenin plus the square root of R Thevenin squared plus X Thevenin plus X2 prime quantity squared like so. And I'll just write down the numbers. 262.808 volts RMS 1 squared. 376.991 radians per second. 0.290 ohms plus the square root of 0.290 ohms squared plus 0.675 ohms. Oh, sorry, I need to add to that 0.510 ohms squared. Close that out, close my bracket. And we get a torque of 181.999, so 182. All right, so literally pretty much the only thing I could think of to ask you guys for that we didn't find here would be the efficiency at maximum torque, which we calculated effectively the exact same way that we did earlier. We would just be calculating things at the slip speed of, excuse me, the slip of 0.161. Since that's going to change, since we have a different slip, so the overall resistance of our rotor changes, which is in turn going to change our rotor current. That change in our rotor current is going to impact the losses in our rotor, which is in turn, so that's going to change our copper losses in our rotor, which is in turn going to change the output power delivered to the shaft, which in turn changes our efficiency. So it's just 4 or 5 steps to get one thing. So anyway, all right, so this is what I expect you guys to know for induction motors. I am seriously considering allowing you guys to just have open notes for your next test because there are just so many damn equations, and we're going to have an equal amount of equations for synchronous machines, which is what we're going to deal with next. I put a homework set up last night. 3 problems. I asked you guys to fill out a poles and synchronous speed table effectively, and then I have you do 2 problems. I'm going to give you another couple of homework problems either this evening or tomorrow evening that'll be due a week from today, covering what we covered in class today effectively. I would definitely won't give you 1 problem with 12 parts. I will give you 2 or 3 problems with 4 parts or so a piece to make it less terrifying, but basically covering the exact same thing we did here. And then we're going to be moving on to synchronous machines next week. So trying to catch back up. Once we knock out synchronous machines, expect to have another test. So somewhere in the ballpark of 2 weeks from now. Yes, Jacob. Go to the end of the previous page.